This is the third and last before school lesson that you're going to need to learn. Sorry you have to do this. These are those times, though, I guess. Um, this one is going to look at a more formal definition of what makes a function continuous or not continuous. And this formal definition is something you're going to need to use from here on out. We've kind of been talking about, oh, that's continuous because it's a nice smooth curve, or that's not continuous because there's a hole in it. But now we're going to put some more formal definition to what makes a function continuous or not. And then based off of the fact that a function is continuous, we're going to look at a theorem that's called the Intermediate Value Theorem. And that Intermediate Value Theorem only works if a function is continuous. So let's get at it. This is the basis of the formal definition of a function being continuous. It's an important concept in calculus. You can read this because many of the theorems of calculus require functions to be continuous, like the intermediate value theorem. Simply stating that you can trace a graph without lifting your pencil is neither a complete nor a formal way to justify the continuity of a function at a point. So in order to justify that a function f is continuous at a point x equals a, you must demonstrate that f meets all three conditions below. Okay, so notice x equals a. If you look in the picture here on the right, x equals a is what we're talking about right there. At that point, is a function continuous or not? So the first thing is, the first part of the formal definition of continuity is that the limit exists. And then notice the little blurb. That means that the limit from the left and the limit from the right are equal to each other. They're both approaching the same value from the right and from the left. Okay, so the limit exists. F of a exists. So that means when we plug a number into the function, we don't get undefined. It's not a hole. It's not a vertical asymptote. The point actually exists on the function. And the third part is that the limit that we found in the first part and the function value that we found in the second part, those two are the same point. Okay, I'm not going to say too much because I need you to pause when I'm done here, and I want you to answer a couple questions. The couple questions are here. Ignore the graph on the right. That's just for the next question, so ignore that. I'm going to move this up just a little bit. Ignore that graph on the right. I want you to answer question 1, parts A, B, and C. I want you to sketch a function that satisfies condition 1, meaning the limit exists, but not condition 2, meaning the point does not exist. So that means that condition 3 doesn't work either because it fails part 2. Okay, and then for part B, I want you to sketch a function that satisfies condition 2, that the point exists, but not 1. So that means the limit 1 exists, even though the point does. And then finally, for part C, sketch a function that satisfies condition 1 and 2, that the limit exists, the point exists, but not 3. Those two values are not the same. I actually want you to pause and go do that now. All right, I hope you've actually gone and tried it. And I said ignore that graph in the lower right, but that graph in the lower right is going to actually be a pretty good thing to look at. If you did, good for you. If not, that's fine. I'm going to sketch an example for all three of those, and we'll talk about why it fails and stuff. So sketch a function that satisfies condition 1 but not 2. So that means the limit exists but the point does not. That is one we looked at almost from the beginning. If I just get really straightforward with this, let's use a fun color. How about this really nice light purple? So if I sketch a function where the limit exists but the point does not exist, I can think of probably the most simple situation I can think of is a linear function that has a hole in it. You can get as crazy as you want. So that means right here when x is a, the limit exists. We're approaching this value from the right, same value from the left. So it satisfies condition 1. The limit as x approaches a exists. However, this one fails option 2 or condition 2 because f of a is a hole. And since f of a has a hole in it, that means the function is undefined at that point. And therefore, part 3, the exists does not equal undefined because the limit exists, but the point is undefined. So it therefore fails the third condition as well. Okay, that's one option. You could have done so many different things, but as long as the limit exists, the point does not. Okay, let's go on to the next one. Sketch a function that satisfies condition 2, but not 1 or 3. So meaning the point exists, but the limit does not. Okay, let's see if we can, again, infinite number of ways. I'm going to go back to that piecewise function we had in the very first video. Let's say this is a, this point exists. However, the limit does not, because we cannot approach that point from the right and from the left. So the limit as x approaches a does not exist. F of a exists. There's a point on that function. It's right here. F of a exists. And then this fails. Part 3 fails as well because does not exist, does not equal exist. Okay, and finally, sketch a function that satisfies conditions 1 and 2, but not condition 3. So the limit exists, the point exists, but they're not the same. We saw an example of that also in the first video. This one, this is probably the most, I'm going to move a, I'm going to put a on that side now just to say that it doesn't have to be positive all the time. Here's the example I love the most. So let's just say we've got a parabola that has a hole. Limit exists. We're approaching the same value from the left as we are from the right. Okay, so condition 1 is met. The limit as x approaches a exists. The point has to exist as well. But I just drew a hole, so how can the point not exist? Or the point exist? If I just do, this is a piecewise function, that just has a point floating in space. So it's a piecewise function. Even though we've got the parabola has a hole in it, we're approaching that same hole, that value from the left and right, but then we've just got a point that's defined up above. So f of a also exists. However, the limit, the value of the limit is not the same as the value of the point. So those two are not the same. Okay, any variation of that is absolutely fine. That's totally fine with me. Okay, now I'm going to give you another question. Now is when that graph comes into play, so I'm going to zoom this back out a little bit. Now it says examine the graph at the right. Now we'll bring that graph in. Identify 4 values of x where a discontinuity exists. At each of these values, state the condition or conditions of continuity that fail. So I'll give you an example of what it's trying to say here. So for example, if we look at -2. So we say the limit, we would say discontinuity at x equals -2. At x equals -2. The limit as x approaches -2 exists. F of -2 exists, but it fails condition 3. the limit as x approaches -2 does not equal f of -2. Just like that last one we did. Okay, so this one fails condition 3 for that reason. Even though the limit exists, the point exists, the two are not equal. So now I want you to pause. I want you to go find 3 other points, and I want you to describe which condition fails, and I want you to actually do this. Don't just wait for me to come back. Go. Okay, welcome back. I hope you did it. Let's look at 3 other points of discontinuity. I'm going to go in order from left to right. So we said discontinuity at x equals -2. The next one I see is at x equals 0. And this one fails condition 1. Since the limit does not exist. From the right, the function is approaching positive infinity. From the left, the function is approaching negative infinity. Those two values are not equal. Okay, let's move on to the next one. The next discontinuity is at x equals 1. Fails condition 1 again, because the limit from the left is approaching 1. However, the limit from the right is approaching 2. So the limit as x approaches 1 also does not exist. We're approaching 2 different values from the right and from the left. And then the final discontinuity is at x equals 2. This one fails condition 2 because the limit exists. The limit as x approaches 2 exists. It approaches, the limit as x approaches 2 is 2. However, f of 2 does not exist. It's undefined. There's a hole there, but no point, like there was on -2. Okay, last thing we're going to talk about then is this theorem, the intermediate value theorem. Explain why a function that is continuous. So here's that important point. This is why we just spent so much time talking about continuity. If we did not talk about continuity, this theorem could not guarantee anything. So this must be true. Explain why a function that is continuous for all values must pass through every y value between f of a and f of b at least once. So that's the intermediate value theorem, saying as long as this function is continuous. So we have f of a. Let's just call this number 1, but not in highlight. Let's use, this is 1 and this is 5. So what the intermediate value theorem says, if f of a is 1 and f of b is 5, then that means f of x will touch every single y value between 1 and 5 at least one time. Let's think about that again. Since this function is continuous, if f of a is 1 and f of b is 5, f of x must have a y value at every single point between 1 and 5. And that makes sense because this function is continuous. There will not be any point where the limit doesn't exist, where the point doesn't exist. This is continuous. Okay, so I call this a well duh theorem because, well, duh, of course, if the function's continuous, it's going to touch every single point. But it's kind of an important thing to note. It's going to come up in some really weird situations. I'm going to do this for one of these, and then I would challenge you to at least look at another one. So this one says, use the intermediate value theorem to explain why each of the following must have a root, or an x-intercept, or a zero, or solution, whatever you want to call it, on the interval. So if we look at 1, for example, we're going to use the intermediate value theorem. So 1 is this function, 1/12 x to the 4th minus x cubed plus 4. And we're saying why on the interval between 1 and 2 must this graph cross the x-axis? That's what we're trying to prove with the intermediate value theorem. Why can we say for sure this will cross the x-axis? Well, first things first, we'd say that since f of x is a polynomial function, it is continuous on the interval 1 to 2. If you don't say this and you don't say it that way, you've just gotten the question wrong. You have to be thorough here. You have to state that you know for a fact that since this is a polynomial, and polynomials are just nice smooth curves, since this is a polynomial, we know this function is continuous. We have to say that. Okay, let's keep going. Let's be more formal. We have to finish this up the formal way. So let's try f of 1. F of 1 is 1/12 times 1 to the 4th minus 1 cubed plus 4. So 1/12 times 1 to the 4th is 1/12 minus 1 cubed, which is minus 1, plus 4. So let's do some of this math. 4 plus 1/12 is 4 and 1/12. Minus 1 is 3 and 1/12. Okay, so far so good. That doesn't help me yet. Let's try f of 2. So we've got 1/12 times 2 to the 4th minus 2 to the 3rd plus 4. Let's see, 2 to the 4th is, oh, Notability just froze up again. Hold on. So 2 to the 4th, sorry, here we go. 2 times 2 is 4, times 2 is 8, times 2 is 16. So we get 16/12. 2 to the 3rd is 8 plus 4. So I can do -8 plus 4, first of all. That's -4. 16/12 reduces to 4/3. If I do 4 minus 4/3, I'll get -2 and 2/3. So why can we say then that this graph is going to cross the x-axis between 1 and 2? Why can we guarantee that? I hope you're thinking about it. I hope you're not waiting. Well, I know that f of 2 is negative. I know that f of 1 is positive. Somewhere on that interval then, that graph must cross the x-axis. In other words, f of something must equal 0 in there somewhere. So here's the way you need to write this out. If you don't write it out this way, you don't get all of the points. This is not a complete answer unless you write it this way. So first things first, you must state that this polynomial is continuous. Secondly, you must say, since f of 2 is less than 0 and f of 1 is greater than 0, the intermediate value theorem guarantees, oh, I always forget how to spell guarantees. Guarantees, I think that's right, that f of x will equal 0 on the interval 1 to 2. Okay, those two parts are really, really important. Since f of x is a polynomial function, it is continuous on the interval from 1 to 2. Must talk about continuity. And then secondly, you need to tell me about the intermediate value theorem. Since f of 2 is less than 0, f of 1 is greater than 0, the intermediate value theorem guarantees that f of x will equal 0 somewhere on that interval. Okay, give a couple more try. I would try the trig ones because I know everybody's afraid of trig, but don't be afraid. Trigonometry is your friend. Give those a try and see what you think. See how it goes. See if you can prove that Hopefully you'll get negative and positive answers. So the important part is talking about why cosine is continuous in number 3. And in number 4, we know that tangent is not a continuous function, but is tangent continuous on that interval from 1 to 4? Okay, have fun with it.